Welcome to a code report solution video. In this video, we're going to be covering the solution to problem 1 from the topcoder TCO18 round 2B contest entitled SubarrayAverages. Averages. The problem states Li Chen has an array of positive integers. You are given its initial state in the array A. Li Chen can modify the array by repeatedly performing the following operation. Choose a contiguous subarray and replace all values in the subarray with their exact average. And the question is asking you to find the lexicographically smallest array Li Chen can obtain by performing a sequence of 0 or more operations. Return A with the elements of that array. And note that our array A will contain between 1 and 10 to the third elements, which means that a quadratic solution will be sufficient, and each element of our array will be between 1 and 10 to the 6. So integers will do. So let's take a look at the explanation of our operation that we can perform that was also provided in the problem statement. So it says, for example, in the current array, if the current array is 1, 3, 2, 4, some ways to perform the operation look as follows. So Li Chen can select the first 3 elements, 1, 3, and 2, and then take the average of those elements 2, and then replace those 3 elements with that average. So your array ends up being 2, 2, 4. Another version of this operation is to select the 2 middle elements. 3 and 2 gives you an average of 2.5 and replace those. She can select all 4 elements, so that's the entire array, and replace this with 2.5, 2.5, etc. And it also notes that multiple operations may modify the same indices in the given array. For example, given the array 1, 4, 2, if Li Chen may use one operation to change it to 1, 3, 3, and then another operation to change this array to 2, 2, 3. So initially it's not clear what algorithm we should use to solve this problem, but the way I found my way to the solution was by taking a look at all of the examples that topcoder provided us with. And if you'll notice, in an increasing array, we don't end up doing any operations. We just return the array that is given. And in a decreasing array, we are going to replace the whole array with the average of all of the elements. So that starts to indicate that our algorithm should have to do something with looping from left to right, and checking sort of every average from your starting point to your current ending point. And then as you do that, you keep track of sort of a running sum, and then you calculate the average at each point, and then you just cache the average at that point that's the lowest, and also sort of the ending point. And then once you finish that first loop from your starting point to the end, you fill or replace all of the elements in between your starting element and the element at which the lowest average occurred. So this is going to end up being a quadratic solution, but because we know we only have up to 1,000 elements, this should do the trick. And that algorithm informs, if you've got increasing, your lowest average is always just going to be the first element, because anytime you add an element to the right, it's going to increase that average. And if you have a decreasing, every time you add an element to the right, it's going to decrease the average. And then when we check that sort of methodology or that algorithm with the remaining examples, you can see that it holds. So because 1 is increasing and you're never going to find anything lower than 1, you know your first element should be 1, so we'll skip that. Then on our second iteration, 2 by itself, its average is 2. Then we go to the next one, 1. That's going to give us 1.5, and then 2 is going to skip back up. So then we would replace the 2 middle elements by 1.5 and 1.5, and then we're just left with 2. So if we walk through Li Chen's array that we were given, 1, 3, 2, and 4. So for our first loop, we're going to start at our first element, and by itself, its average is just 1. If we move to include the next element, the average is going to be 1.5. So this is not lexicographically smaller. So lexicographically just means the way you would find something in a dictionary. So if you pretended these were letters, A, C, B, D, which way could we sort of arrange these so that we get the smallest word, or the word that you would find first in a dictionary. So 1 is less than 1.5, so this is lexicographically smaller than our second example. If we move to include the first 3 elements, our average is going to be 2, and so you'll end up with 224, and if we include all 4, you're going to end up with 2.5 throughout. So of these 4, the lowest average that we get is just by taking the first element, so we're going to lock that in and then change our next starting element to be 1 more than what our ending element was here. So then we look at this by itself. 3 has an average of 3, obviously, including the next element 2. It has an average of 2.5, and if we include all 3, we get 1, 3, 3, 3. So of these 3, the lowest average is 2.5, which makes this array the lexicographically smallest, and we're going to lock in replacing 3 and 2 with 2.5. And we only have 1 element left, so we know that this is just going to take the average of itself, and this is going to be our final array. So that's our algorithm. It's pretty straightforward once you identify sort of that's the pattern. So let's take a look at our code. So here we have a function called findBest. It takes a vector of integers as its parameter, that's called a, and then it's going to return a vector of doubles. And so at the top here, we are just declaring a vector of doubles. We're going to call it B, and we're basically going to copy all the elements of A into the array B, or the vector B. And then up front, we are going to declare 2 iterators, one starting, or both of them starting to the pointing to the start of the array. And so we're going to have our first loop while start is not equal to the last element in B. We are going to continue to do this loop, and then inside we are going to initialize 2 doubles, sum and average underscore I, which means the average at this point I, and also another iterator, which is just going to point to whatever our start, or sorry, another double that's going to take the value that is at our start iterator. And then we are going to loop from start, that's our current start of our range, to the end, and at each point we're going to do a plus equals to sum, adding the value that we're currently at, and then we're going to calculate sort of the temporary average, so the average at our point I, and we're just going to do this by taking the running sum that we just calculated and then dividing it by the number of elements in that sort of range. So we get that by doing distance between start, our current iterator I, plus 1. And once we do this, we just check, is our average at this point I less than our average that we've calculated up to this point? If so, reset our average and set our end iterator to bi. And so once we've finished this for loop, we're going to have identified our smallest average and the iterator, the position at which this average is achieved. And so we do a post increment on end because that's not going to be included in our fill algorithm. And then once we do this, we just call our fill algorithm between start and end and fill the average. And at this point, we can then reset our start iterator to be equal to n, because we know that we've in that range found the optimal average to be filled, so we don't need to check that again. And so once we do this for one iteration, we're going to continue to do this until start is equal to the past the last element, and then we can just return our vector of doubles. So the last thing to do is talk about the time complexity, and as mentioned a couple times before, this is going to be quadratic due to our nested for loops. And also thanks to Dennis for code reviewing this solution.
As always, if you enjoyed this video and found it helpful, hit that like button. If you want to see more, make sure to hit that subscribe button. You can follow me on Twitter for reminders 30 minutes before contests start, and you can find all of the code shown in my videos on my GitHub page. Thanks for watching, and I'll see you in the next video.